3.2 looks at calculus of vector-valued functions. So, like scalar functions, the derivative of a vector-valued function r of t is defined as r prime of t is equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t divided by delta t. So it's the same as the derivative of a scalar valued function. So we get this, and we can use all of the usual derivative rules. So let's look at an example. Suppose we had the function r of t is equal to t squared 3t plus 1 and sine t. Well, its derivative then, r prime of t, would be what we get just by taking the derivatives component-wise. So it would be 2t, 3, and derivative of sine is cosine. Let's do another one. Let's say we have r of t is equal to e to the ti plus natural log of t, j. Well, r prime of t is going to be e to the ti plus derivative of natural log is 1 over t, so 1 over tj. Now, the textbook has a list of all the rules that we can use for derivatives of vector-valued functions, and I want to point out two of them in particular. The two I want to look at are the product rule, because when we're dealing with vector-valued functions, we have a product rule for both the dot product and the cross product. And let's look at them. They're exactly what you would expect. The derivative d dt of r dot u is equal to r prime u plus r u prime. And these are both dot products in here. So it's r prime dot u plus r dot u prime. Now, when I do the product rule, usually I say first times derivative of the second plus second times derivative of the first, but that's not good here. What you want to do, well, it's okay for the dot product, but it's not good for the cross product. The cross product, we have to do r prime u plus r u prime, and these are cross products. It's important to get the order correct here, because if you get a cross product backward, like if you did a u prime cross r here, it would be the negative of this. So the order is important.